Dr. B here, and this is the story of Bohr's epiphany. Niels Bohr was a Danish scientist who did most of his work in the early 20th century. And around that time, it was known that atoms existed. It was known that electrons existed, thanks to the work of J.J. Thomson and others, and it was known due to the work of Rutherford and his graduate students, especially, that the electron existed outside the nucleus. But what was it doing? That's his story. That's where Bohr came into play. It was observed that if you take elements and ionize them, turn them into a plasma, which is not hard to do, they will, if you put them through a prism, they'll emit some unique sharp lines. So those lines are there for each of the pure elements, and they're like a fingerprint. But nobody knew what those lines were due to or what significance they had. Bohr knew that the hydrogen emission spectrum only gave 4 visible lines, varying from 656 to 410 nanometers. What was the significance of that? There was some information available to him due to the work of some mathematicians, where they investigated those lines and said maybe there's a pattern to it. 656, 46, 434, 410. Why those wavelengths? Well, they found that if you look at those 4 numbers, and perhaps they had some other numbers as well, perhaps they had from infrared or some UV numbers, I would guess. 4 numbers isn't much to go on. But they found that there's a pattern to that sequence. What is the pattern? If you take that wavelength, it's the product of 1 over a number times 1 over a whole number minus 1 over another whole number. How they figured that out, I'll leave that to someone else, but that is known as the Bohrs formula, and this number is known as the Rydberg constant. But let's go ahead and calculate it for 3 and 2. We should get one of those numbers. These numbers, which we're going to call inner and outer, which is a bit of a reveal, have to be integers. So let's make the inner, that means the lower number, 2, and this number 3. So we've got, let's see, 1/4 minus a ninth. 0.25 minus 0.11, that's about 0.14. 100th of that is 0.0014. The inverse of that is going to be between 500 and 1,000 somewhere, right? 1 over 0.000 something. And in fact, that is 656, and there's your first number. You try it with other small integers, you'll get the rest of them. Isn't that interesting? And that's fine, but maybe it has some meaning. Bohr recognized in a moment of epiphany that those numbers could simply be locations where the electrons exist. He's saying to himself, okay, there it is for visible light. It always seems to go to the second shell. That's when you get numbers between 400 and 700. N is just some integer, right? And there's the numbers that lead to those observed wavelengths of visible light for the hydrogen plasma. Maybe it's a very simple story. Here it is going from 2 to 1. The electron simply is descending from the second shell to the first shell, and as it does that, it emits a particle of light known as a photon. Electron emission creates light. This is the Bohr model of the electron. Electrons reside in shells, according to him, and they go to higher energy shells. As they proceed from a higher energy shell to a lower energy shell, they emit packets of light known as photons. What's the evidence for it? This calculation. It's a convincing calculation that seems to be very true. Let's go ahead and see if it fits. Say we are going from the third shell, from the first shell. What color of light gets emitted? None. You're going to a higher energy state. You're absorbing energy. However, if we go from the third shell to the second shell, we can plug it into the Bohrs formula, and we'll see that this emits red light. If we go from the fourth shell to the second shell, run your calculation, and it's a teal sort of color. Very beautiful. You can demonstrate these lines in any simple classroom if you have the right gear. It doesn't require much. Fifth shell to the second shell, That's blue light. You can even go from the 6th shell, and you're now at the edge of what's visible at about 410 nanometers. If you have the right equipment, you can do the same thing for the infrared series, and interestingly, you always end up in the 3rd shell. You can also do it for the ultraviolet light, which always ends up in the 1st shell. Hey, you can pick any shell to any shell, you get a wavelength, and you'll be able to observe it. This is consistent with observation, extremely strong evidence that electrons seem to reside in shells. If only it were so simple. This does seem to work for hydrogen. When you take it to multi-electron systems, such as helium, things get more complex. This is Bohr and his moment of epiphany.